Hello students, in this video we'll discuss the Cauchy-Schwarz inequality for inner product spaces. Let's suppose that x and y are in Rn, our vectors in Rn. Then, recall, we have the dot product of these vectors, x dot y is just x1, y1 plus xn, yn. And then we have that the norm of x squared is just x dot x. So I want to find some inequality that relates norms to inner products to each other. And this is the Cauchy-Schwarz inequality. So we have the Cauchy-Schwarz inequality. And that says the following. It says that the absolute value of x dot y, that's a scalar quantity, is no more than the product of the norms, the norm of x and the norm of y. Okay? So let's prove this inequality. And so the idea is the following is to consider a quadratic function. Use the convexity of these functions over here. So we're really going to use convexity. So the proof, it goes as follows. So proof, consider phi of t. And phi of t is just going to be the norm of x minus t y quantity squared. Okay? We're going to show this a quadratic function of t, and we're going to find the minimum of this quadratic function. Okay? So this, of course, is what? This is nothing more than x minus t y dot x minus t y. Okay? And if we FOIL this out, which we're allowed to do by properties of inner products, what we're going to get? We're going to get x dot x minus, then the cross terms are going to be a y dot x and an x dot y. Those are the same by the fact that the norm is commutative. In a real inner product space, for complex inner product space, we're going to put conjugates over here. So we have minus 2t x dot y, and then a t and a t is a t squared, and then y dot y. Okay? And now the key feature is that therefore this phi of t, thus phi of t is this quadratic function. Phi of t is equal to t squared length of y quantity squared minus 2t the inner product of x and y, and then plus the length of x quantity squared. Okay, and the key is that this is a quadratic function in t. So this expression over here is quadratic in t. Okay? And moreover, this function, since it's a norm squared, is always greater than or equal to 0. So this function is always greater than or equal to 0 because it's a norm, right? And norms are greater than or equal to 0. And so now what I want to do is I want to say, well, this is basically, if we think about this as a parabola, so what we have over here is we have this parabola, this graph over here. There's the t-axis, there's the phi axis. And so we have one of many things. It could be a parabola like this. It could be a parabola like this. It could be a parabola like this that actually hits t equals, that actually attains the value 0, right? So it can be any one of these parabolas over here. What it cannot be is it can't be any parabola that's pointing down and going into the negative part of the phi axis, right? So it's parabolas that have this form over here. So any one of these parabolas will work over here. So that's what my function phi looks like. It's one of these things over here. Okay, great. And so where does the minimum occur? Well, the minimum occurs when the derivative is equal to 0. So let's set the derivative equal to 0, and this will allow us to find the minimum. So the derivative is going to be 2t length of y squared minus twice the inner product of x and y, or the dot product of x and y. And if I solve this, what we're going to see that this tells me over here, solving this, that tells me that t minimum, the minimum value of t, the t that minimizes this expression, that minimizes phi, is exactly equal to what? So that's going to be x times x dot y. The 2's are going to cancel out. It's going to be x dot y over the length of y quantity squared. Okay, excellent. Now let's plug this into the expression over here. So therefore, 0 is greater than or equal to phi at t min. Okay? Now what is phi going to be at t min? Well, let's just plug it into the expression. So it's going to be x dot y quantity squared, x dot y quantity squared. And then we're going to have a what? We're going to have this is going to be a t squared. So I'm going to have y to the fourth and y squared. That's going to give me a total cumulative factor of y, length of y squared in the denominator. Right? Because I have a y to the fourth and a y squared in the numerator. That's a y squared minus 2 times t, which is going to be an x dot y over the length of y squared. Okay, and then that's times x dot y, times x dot y. And then finally, the length of x squared, right? The length of x squared, okay? So this expression is always not negative over here, so what we can see is the following. We can see that there's going to be a total factor of what? So over here, this is going to be a minus, this is going to be a total of a minus x dot y quantity squared over the length of y squared. So these two terms are going to simplify. So these two terms over here just simplify to what? Just going to be simplified to negative x dot y over the length of y squared. And so what that allows me to do is I'm going to throw that on the other side of the inequality, and this tells me that x dot y quantity squared over the length of y quantity squared is less than or equal to x squared. And therefore, this tells me that by taking the square root of this inequality over here, taking the square root of this inequality, I'm allowed to assume, I can conclude that the absolute value of x dot y is no more than the length of x, the length of y. And that's the proof of Cauchy-Schwarz. Now, I get one other bit of useful information from this, and that's the following. What I can say is I can say, well, when does actually phi attain 0? So phi of t is equal to 0. Phi of t min is equal to 0 if and only if phi is equal to 0 at some point. If and only if x minus t min y is equal to 0, and we know that the norm is equal to 0 if and only if the expression inside the norm is equal to 0. So that says that x is equal to t min y, and that says that x is parallel to y. So equality happens, equality in this in Cauchy-Schwarz if and only if what? If and only if x is a multiple of y is lambda times y. So in other words, if x and y are in the same direction, Cauchy-Schwarz gives you equality. Now there are lots of like cute applications of Cauchy-Schwarz. So one cute application is the following. If you look at 1 plus 2 plus 3 plus n, so here's an example of Cauchy-Schwarz, this can be written as 1 times 1 plus 2 times 1 plus n times 1, for example, right? And now I have a dot product over here. I have the dot product of 1, 1, 1, 1, 1 with 1 through n, right? So this is 1, 1, all the way up to 1, dot 1, 2, all the way up to n. And so Cauchy-Schwarz says that this quantity over here is less than or equal to what? Less than or equal to the square root of the sum of the square of those things, which is root n. And then the square root of 1 squared plus 2 squared plus n squared over here. So I get this cheap inequality. So if I square this over here, we can conclude, therefore, that 1 plus 2 plus all the way up to n quantity squared over n is less than or equal to 1 squared plus 2 squared plus all the way up to n squared. So this is one of a ton of inequalities we get from Cauchy-Schwarz. It's a very powerful geometric device which allows me to prove a wide variety of convex inequalities that typically relate to the LP norms of sequences or the LP norms of certain geometric quantities that occur oftentimes when we're studying the triangle inequality or we're studying properties of quadrilaterals or cyclic quadrilaterals. There are many, many applications of Cauchy-Schwarz which you'll see in further videos. Thank you very much.